So in this talk, I want to explore the sorts of structures that we see inside of neural network loss functions and some of the implications that it has for the design of optimization algorithms. And so just to start fairly basic and to be clear about what we're talking about, a neural net, at least in the computer vision context, it takes in some image. If it's sampled from the internet, it's probably a cat or something like that. You pass it through a bunch of convolutional filters and it spits out a label. So in this case, it says we're looking at Grumpy Cat. And so you can think in some abstract sense of a neural network as a function that maps images, X, onto labels, Y. And it has some set of parameters, W, that are called the weights. And the way that we train these neural networks is by minimizing a loss function. So we collect a whole bunch of these X's and Y's, and then we have a loss function that penalizes the difference between f of X and Y. So you might pick something like a least squares loss, or in the more sophisticated context, like what we'll look at later, we use something like a cross entropy loss. But the point is that the loss function, the loss function is a function of the weight parameters. So when I say the loss function has a very high dimensionality, it does not have the dimensionality of the input features. And also, it's very expensive to evaluate the loss function because you have to average over all of the data points in your training set, and that could potentially be very large. So if f was a linear function, then this would just simply be a least squares problem, linear least squares problem. This would be a convex quadratic loss function. Everything would be fine. But these neural networks, they have nonlinearities layered on top of nonlinearities, and so you would think that this would be a very, very non-convex loss function. But the question is how convex. We know that we can minimize these things fairly easily. Oftentimes we minimize these things and we get global minimizers. And so maybe it's not so non-convex. But at the same time, the sophisticated structure of this function would lead you to think that it is. So how non-convex is it? There's been a lot of theoretical work on this. And I'll just mention sort of categories of results that people have been able to prove. So there are theoretical results that say that local minima are not so bad. So if you get a local minima, it's not too far an objective value from a global minimizer. There are results that show there are no local minimizers under various assumptions. For example, if your neurons are linear, so there's no nonlinearity, or you have certain very wide layers or full rank structure in the weights. And there's also a variety of results that show that you won't have local minima for certain types of shallow nets, so neural nets with one hidden layer, for example. But this is an area where we mostly rely on theory. And the reason we rely on theory is that evaluating the loss function is really expensive. You have to loop over the entire training data set. You have to do a full epoch of computation just to evaluate the loss function once. And so it's really hard to see what these things look like. I've been interested in this problem for a long time, and I've had a lot of discussions with my grad students on solutions to this problem. We can investigate the loss function with harmonic analysis or random matrix theory or statistical mechanics. But you have this fundamental problem that even with a GPU, it's too expensive to plot the loss function. But grad students don't like to do harmonic analysis. So I gave this problem to my grad students, and they came back with their own solution, which is more GPUs. And so we did a bunch of loss function computations on a GPU cluster, and we were actually able to produce visualizations of these loss functions, and they look like this. So this is the loss function of a 56-layer neural network trained on the CIFAR-10 data set. Okay? So we're going to look at a bunch of these loss functions, and we'll talk about how things like neural network architecture design affects the structure of these loss functions. But first, I want to talk about our motivations and a little bit of background on how you visualize these things and how to interpret the visualizations. So one of the things that motivated us to look at this problem is there's this debate going on. I call it the sharp versus flat dilemma. So it is widely believed that flat minimizers of neural networks generalize better than sharp minimizers. Flat means it looks more like this, so it has a really wide basin. Sharp minimizers look like this. They have a really narrow basin. And there's a variety of theoretical works and empirical works that have been done that suggest that flat minimizers generalize better than sharp minimizers. And in fact, Pratik Chaudhry talked earlier today about some of his entropy SGD bounds that provide a nice way of measuring the flatness of some of these minimizers. But this is sort of up for debate. There was a recent paper at ICML 2017 that exploits certain types of scaling invariances that we'll talk about in a bit to show that sharp minimizers can also generalize. And sharp versus flat is really important because the kinds of algorithms that we use to train affect what kind of minimizers we get. So it's believed that the implicit regularization of SGD is important. That means we need to have noise in SGD. And so small batch sizes tend to give us flat minimizers. The SGD optimizer tends to give us flat minimizers. But then there are also bad optimization methods in some sense. For example, big batch optimization or using the atom optimizer tends to result in sharper minimizers that don't generalize as well. Okay, so this is a simple experiment that's appeared in the literature. And it shows some of the caveats of visualizing loss landscapes. So we'll do an experiment. Let's start with a weight vector. So this is in weight space, or in a very high dimensional space. We'll start with some random initialization. And we're going to train our neural network twice. We'll train it with a small batch, and we'll go along some path and find a small batch minimizer. And we'll train it with a large batch, and we'll look to see the large batch minimizer. And the thought is that the small batch minimizer is going to be flatter and generalize better, and the large batch minimizer is going to be sharper and generalize worse. And there's been a number of papers that have used visualization of this type. There's Dan M and Ian Good. Dan M has a paper on this, and Ian Goodfellow has a paper where they do similar types of visualizations. And so what we do is we take these two minimizers and we pass a line through them. So this is a line that interpolates between these 2 points in weight space. And then we're going to walk along that line, and we're going to plot the loss function at every one of those locations. And we get something that looks like this. So the red line at the top, this is plotting accuracy. You can just focus on these blue lines. These plot the loss function. Solid line is the training loss. The dotted line is a little bit higher. That's the test loss. So you look over here. The small batch minimizer has this really wide flat minimizer. So that's nice. And then we look over here at the large batch minimizer, and it kind of comes down here like a needle and shoots back up. So it's really, really sharp. And so it's very apparent that there's a sharpness difference between these two things. So one of the students in my lab, Hao Li, ran this experiment, and we replicated the results from these papers. But then he started turning some knobs, and weird things start to happen. So he turned on weight decay. And when you turn on weight decay, which is like an L2 penalty on the size of the weights, you get a completely opposite result. So with weight decay, now the small batch minimizer is really sharp, and the large batch minimizer is noticeably flatter. But it doesn't really change Sorry, is the question?
Here, when you say wide and flat, it's only projected on a one-dimensional.
It's only projected on a one-dimensional vector.
So we have no idea how wide or how flat it is in the other direction.
No. But that's one of the caveats of this method. But so these plots can be a little bit deceiving, which is sort of the point of looking at these two different scenarios. Okay, so still, the small batch minimizer generalizes better, but it's way sharper than this large batch minimizer. So what's going on? So it turns out that what you're really plotting is not the sharpness or flatness of these minimizers. What you're plotting is just the size of the weights. So we look at a histogram of the weights. And here you'll see this blue histogram shows the weights for the small batch minimizer. And the weights are really large, so this histogram is really spread out. And when we use a large batch, the histogram concentrates more toward the origin, and you get smaller weights. So what happens is, when your weights are small, so let's say that your weights are about size 1, if you add a perturbation of size 10 to them, that makes a huge difference, and it destroys the performance of your neural net. But if your weights live on the scale between 0 and 100, adding a permutation of size 10 might not be so disastrous. And so when the weights are big, the loss function doesn't depend so much on small permutations. When the weights are small, it depends a lot. And so when the weights are small, you get these really sharp-looking minimizers. When the weights are big, it looks flat. Okay? But this difference in size scale, it doesn't correlate at all with generalization error. We saw here that we had a good generalization error from the sharp minimizer. And in general, we don't really care about how big the weights are because of the scale invariance property. So if you have a neural net with ReLU, yeah?
Shouldn't the weight decay have made the weights even smaller?
Yes, it did. Oh, sorry, let me go back. It did.
Would it have made it even sharper?
Well, they are relatively sharper, right? I mean, this flat minimizer is still quite a bit sharper than this one.
I guess I'm thinking about compared to, so for sure in the left side peak is sharper, but the right side you're noting is wider, or flatter. But the weight decay shouldn't have, by that idea, shouldn't have been even sharper?
Oh, sorry, I'm not sure which one you're referring to.
The right.
This one?
Yeah.
Shouldn't have it been, that's interesting. Yeah. It doesn't, with the large batch, okay, well, there's a reason why you sort of flip the balance by turning on weight decay. It's because weight decay doesn't really affect large batches very much because we train these neural nets for the same number of epochs. And when you have a really large batch, that doesn't generate very many updates. There's not very many updates per epoch. When you have a small batch, you have lots and lots and lots and lots of updates. So it doesn't really, you might expect this to look a little bit sharper than it does. But actually, the weight decay doesn't really affect the size of these weights as much as you would think when the batch is large. But these are two completely different sets of minimizers. We're not plotting the same minimizer between the two, so they don't necessarily have to be the same. They don't even have to be comparable. We'll see later when we do sort of a more normalized visualization, comparisons across these different weight decay scenarios make sense. Like you can correlate sharpness with generalization error. Okay, so there's a scale invariance property. If you use ReLU nonlinearities, then I can pull out the weights in one layer and multiply them by 10. And I can compensate that by multiplying the weights in another layer by 1/10, so I can divide by 10. And when I do that, you get the exact same thing out of the network that you did before. So you get an equivalent neural network. And when you use batch normalization, so batch normalization takes the outputs from a layer, and it subtracts the mean and divides by the standard deviation, and renormalizes everything. So in that case, the weight scaling is completely irrelevant. You can multiply the weights by 100, and that factor of 100 would just get taken out by the batch normalization layer. And so these differences in scaling, they're not really a meaningful thing to visualize. They don't really affect the performance of the neural network. And it's not really, these sorts of simple plots aren't really visualizing the endogenous sharpness or flatness of these curves, so they can be very misleading. Right? All we're really visualizing in this case, it's some combination of the true sharpness and flatness combined with the scaling of the weights. So how can we get a more meaningful measure of sharpness? So we propose something called a filter normalization. It's just a very simple normalization scheme to sort of normalize the different scales between minimizers. And the way that we're going to make these two-dimensional plots is like this. So we'll start by training a neural network. So we start with some random initialization. We train down the contours of our neural network until we get a minimizer. So we find some minimizer. And then we take two random directions in weight space, so two random vectors, and we slice through that point. And those should be roughly orthogonal. And so these two random directions define a plane in weight space. And then what we do is we apply a filter normalization to these random directions, and I'll describe what that means in a sec. And then we just raster over this plane in 2D space, so we just scan over it, and we compute many, many loss function evaluations, and that produces a visualization of the loss function. Okay, so what do I mean by this filter normalization? So the filter normalization, we look at our neural network, and we select out a filter. So we take a convolutional filter out, and I look at this filter, and I say, okay, this filter has magnitude 10. So the 2 norm of that magnitude is 10. But then when I produce my random directions, the random direction that I produce, so just random Gaussian variables, I had to produce a set of random variables with the same dimensions as this filter, and that had a different norm. That had norm 20. And I want those to be comparable. I don't want to be adding a huge perturbation to small weights, and I don't want to be adding a small perturbation to huge weights. So I'm going to multiply that by 1/2, and that brings the norm down to 10. And now I have a direction that is same. So it lives on the same distance scale as the filter that it's modifying. Okay? So as a sanity check, does this actually identify the correct distance scale for these problems? Is this a reasonable way to, with these random directions and filter normalization, to plot these loss functions? And we find that with filter normalization, we actually get curvatures, sharpness versus flatness measures, at least visually, that correlate really well with the differences in generalization that you predict in theory. So this is plotting through a random line, so a random direction through a minimizer obtained via SGD with batch size 128 and with batch size 4096. 4096, it gets sharper, and there's an increase in generalization error. So that minimizer is a little bit worse. We can do the same thing with weight decay. So in this case, I turned on weight decay. If you look at these two minimizers, this one's a little bit sharper than this one. This minimizer is a little bit wider, and it also does a little bit better in terms of generalization error. And we can even compare across minimizers. So here's ATOM versus SGD. This ATOM minimizer is visually sharper than this SGD minimizer, and it also has worse generalization error. So with this filter normalization process, we can, it sort of identifies the natural distance scale of these things so that we can actually compare different minimizers to each other. Okay, so now we have this reasonable way to plot two different minimizers and put them side by side and compare the two. And so we can use this to explore what minimizers look like when you do things like change the optimizer or change the structure of your neural network. And there's different kinds of neural networks we want to look into. The simplest neural networks are what I call VGG-like nets. VGG-like networks are very simple convolutional networks. We do include batch normalization, but it's alternating between convolutions, batch normalizations, and ReLUs. And then we're also interested in skip connection networks, things like ResNets. So ResNets will have connections where information from shallower layers skips over all of these convolutions and gets added into the outputs from deeper convolutional layers. Okay, so this is a 56-layer VGG-like net. So it's a very simple neural network. And you can see that, so this is plotting with two random directions. And at the center of the plot is the minimizer. So there's a minimizer, and you can see that in 2 dimensions, we can actually really effectively visualize the non-convexity of these landscapes. There is a convex attractor here, but it's surrounded by a very hazardous landscape. And one of the most surprising things about these experiments is if you just change the neural architecture, so we're going to add skip connections, and then the loss surface looks like this. So these skip connections radically change the behavior of the loss surface. I can do a side-by-side comparison here. And we know that it's much easier to train deep networks when we have skip connections. All of the modern state-of-the-art networks that manage to get good results on SciFar with really deep architectures really utilize sorts of skip connections. Yeah, Arthur. Right. In some sense, this is the whole landscape in the following sense. So you generate a filter normalized direction, okay? So that should give you a natural distance scale for the problem. And then we go 1 unit in each direction times that direction, okay? So when you get all the way out to the edge here, you've added 1 full filter normalized perturbation to the weights. So you've added a perturbation that's the same magnitude as the weights. So that's pretty far. If you look at this loss surface, you'll see it starts to curl up at the edges here. And we've actually done experiments where we zoom out and look even further. And this loss surface actually starts to shoot up, and it just goes up and up and up monotonically until you just get nans and you can't even evaluate anymore. So there's no more interesting behavior. Yeah. Yes.
Is there another really deep trough?
We don't see any other really deep troughs. These are actually on a logarithmic scale, so that makes this appear a little bit artificially deeper than it is. On a non-logarithmic scale, it's not as dramatic, but then it's hard to sort of capture some of this stuff. But if you zoom out, this one's actually cropped down a little bit. If you zoom out, this one also explodes up. So these are, the problem is if you actually go out far enough that the edges of this thing come up, you can't see into the loss function anymore because it blocks you. So this is sort of trimmed a little bit, yeah. Yep. Right. So I don't make any claims about there being local minimizers here. These don't have to be minimizers. They look like minimizers in 2D, but there could be little wormholes in here that sort of escape to other attractors. These don't have to be minimizers, right? So what I'm really more interested in is convexity versus non-convexity, right? A convex function has convex contours. And if you dimensionality reduce it severely, it'll still have convex contours. So I think one thing that you can take away from these dimensionality reductions is that there's a substantial non-convexity here that you can visualize that isn't present in these more well-behaved networks. We'll see later on, we'll see some examples where that non-convexity creeps back in. Yeah? Yeah. Yep.
shape solution.
Yeah.
Because you have products of weight, so that's inevitable.
Yep. I think you need to be careful how you interpret them. And there are some interesting differences that I'll point out later. But it has more to do with, what I take away from these is more that it's not that there aren't other minimizers, because there are. It's that this landscape is populated with very large convex-like attractors that have very wide basins. Whereas this landscape is populated by a lot of more poorly conditioned, I guess, curvy parts. I don't necessarily want to say local minima.
Most of the dimensions of flat and either are very degenerate.
Mm-hmm.
So again, that's
Right.
I
I think you need to be careful how you interpret these. Because like you said, there could be a lot of dimensions, and there probably are many dimensions in which this is flat. But I still think it's pretty undeniable that there are major quantitative differences here between these two minimizers. And we'll see there's interesting implications for that, too. Yeah?
So the two dimensions that you show are on the same layer, right? It's just you fix a particular layer.
No, this is on everything.
But you're only showing two, right?
No, I'm showing everything. So I take,
So
you take two random directions in weight space that perturb everything. Yeah, you take everything.
I see. And here on the resonant is the same thing. I see.
Yeah. Yeah.
The way that this sort of probe is circumventing high dimension is to take the basis of every possible direction and then look at all the possible planes and do this for all pairwise directions. And that's how you define the cheap curvature, scalar curvature.
Mm-hmm.
So that would get around the problem that you're actually choosing two planes.
Yeah. One of the things I like about the random planes, so later on we're actually going to not use random planes. We'll use certain kinds of PCA directions that capture in some sense the most important directions. The thing is that if you start somewhere on a loss surface, people have done experiments where you plot the loss function over time as you descend down the loss surface. And you see effectively no non-convexity. It's just a monotonic decrease to the minimizer. The problem is that if you don't select random directions, if I pick special directions, so if I stand on a loss surface and I pick to plot in a gradient direction, it always goes down. It's really steep, right? So things tend to be really well behaved in those gradient directions. So if you make those kinds of plots, you don't see the non-convex behavior. And there have been 1D visualizations in the literature that fail to capture any of the non-convexity at all. But that's because if you cherry pick your directions too much, you can't see the difference in behavior of these loss surfaces. But it is there. Like I said, you should take these with a grain of salt because it is a big dimensionality reduction. And later on, we'll see loss surfaces that look quite a bit different when we use PCA directions. Yeah. Oh, I forget how many. This is it's on the order of 10 million. Yep. Okay. All right. So it's the behavior that we see in these loss surfaces is a little bit more complicated than chaotic versus non-chaotic. And in fact, there's an interesting sort of chaos transition that happens that doesn't take place until you get deep enough. Okay, so this is a function. This is the loss surface of a 9-layer VGG-like network. And you'll see it's a pretty well-behaved convex function. And we can increase that all the way up to about 20 layers. And it doesn't really change the qualitative behavior of this loss function at all. It stays about the same. In the original VGG paper, they have 2 networks that were released by the visual graphics group. And there's a VGG 16 and VGG 19. And for depths beyond 19, they found that there was a degradation in the performance. One of the interesting things, if we go beyond 20, then we get into this region where there's sort of a phase transition between these sorts of nice convex behaviors and these sorts of chaotic behaviors. So suddenly the loss surface becomes chaotic. And if we keep going, it only gets more chaotic, although not dramatically so. So this is a 110-layer network. And you'll see there's a very chaotic landscape around a very sharp minimizer. And so there's some sort of phase transition behavior that occurs here. When you get deep enough, there's this spontaneous transition from this sort of convex behavior to this sort of chaotic behavior. That also seems to correspond to an increase in generalization error. And one of the interesting things in these plots is there's a contour in these plots that I like to call the shattering contour. So there's this problem called the shattered gradients problem. If you try to train a network that's too deep and isn't well behaved, you run into a situation where the gradients that you produce from different mini batches aren't correlated. The gradients effectively become random. And once that happens, neural networks are basically untrainable. You can't find good minimizers anymore. So for CIFAR 10, which is what we're looking at here, when you do a random initialization, a good random initialization, you initialize with a loss value of about 2.5. And there's a reason for that. It's because if you put a good initializations, the weights are scaled so that the outputs from each layer look like mean 0, standard deviation 1 Gaussian noise. And if you put that kind of noise into a softmax layer, you get a loss value out of about 2.5. And so when we have this nice convex-like landscape, the 2.5 contour is here. It's well within this well-behaved region. And then as we move more in the chaotic direction, this chaos landscape starts to sort of drop down lower and lower. And by the time you get to 110, the 2.5 contour is right here. It's right on the boundary between this convex-like attractor and the chaotic landscape. And then if you go beyond this, the network becomes untrainable. We can no longer find good minimizers, and this sort of visualization method fails. So I suspect that what's happening is that as this becomes more chaotic, this chaotic region, so there's this partitioning between this well-behaved region and this chaos area. When the chaotic region drops down below this shattering contour, you run into shattered gradients and you can no longer train. So initialization methods seem to fail in that case. You end up initializing way out in this chaos landscape. Yep. That's a great question. Yes. So let's add skip connections. When we add skip connections, that completely prevents this chaos transition from happening, at least for deep enough networks that are fairly deep. We've tried this up to about 300 layers. We haven't gone deeper than that because we've sort of run out of memory on our GPUs. When you add these skip connections, you'll see that there isn't a substantial qualitative difference between these landscapes. If you go from 20 to 56 to 110, qualitatively, these are not, they're very similar. And so if there is a chaos transition, it's got to be somewhere way out here. Yeah?
Is this a symptom or a cause of the resulting problem?
Sorry, what's the question?
Is this a symptom or a cause of resulting problems in the model?
I'm not sure how to answer that. I mean, it seems like it is a property of the model. Some neural networks are well behaved, and we can train very deep, say, ResNets, right? Some neural networks are not well behaved. And I believe pretty strongly that the difference between these networks has to have to do with the loss landscape, because the training, the optimization when you train takes place on the loss landscape. I guess whether it's a symptom or a cause, I don't know. But I think well-designed neural networks seem to be designed, at least implicitly, so that they have loss landscapes that are populated by very wide convex attractors instead of these sort of chaotic regions. Yeah?
So is it that the ResNet is better adapted to images, and so therefore the loss surface is better, nicer, because the adaptive bias of the ResNet architecture matches images and then we train on images like that? Or is it that the ResNet architecture, because it's a connection, is inherently better suited to conditions? When you were training on random stuff, it would still look better.
Yeah, my intuition is it's the latter. It has to do with the conditioning. And in fact, if you look at this minimizer, it's really interesting because this is not such a well-conditioned minimizer. It looks like it has a condition number of about 3. And there's theoretical reasons to believe when you do these dimensionality reductions, you actually compress the condition number by a factor of about 1,000. And I can talk to you about why. But this is like a condition number that's probably on the order of about 10,000. But is that because it's paired with the structure of a convnet, right, for an image? I don't know. I don't know. We haven't tried that. That's a really interesting thing to try, though. I don't really know. I have no intuition for what you would get. That's an interesting question. Yeah. Okay. So if you're still not convinced that there are qualitative differences between these landscapes, this is the loss landscape of that VGG-like network with 110 layers. And you'll see that there's basically a mountain range that passes through this region. And there's like a little, so the colors, it's red is high, blue is low. And there's like a little blue lake sort of nestled in this valley with this big mountain range sweeping around it. If you compare that to something like DENSENET, this is a 121 layer DENSENET, it's so smooth, at least in 2 dimensions, it's basically a parabola. It has no visible convexity at all. So DENSENET has a very sophisticated set of skip connections, many more skip connections than you have in a residual network. And so it really seems like these skip connections are sort of the secret sauce that makes these loss landscapes well behaved. Another thing that we've looked at is how does the width of the network affect the loss landscape. And so if we look at this 56-layer network again, so here's with residual skip connections, here's without skip connections. You can relax this considerably by making it wider. So if we double the width, you'll see that we go from a fairly chaotic landscape back to a fairly well-behaved landscape. And if we go to 4x wider, then we relax it even more. And beyond this, the structure of the loss function actually doesn't change much. Our paper, we go to 8, and it looks very similar to this. And so this is interesting implications, I think. One of my students, Hao Li, used to work on compressing neural networks. He used to work on weight pruning. And one of the things that's well known in weight pruning literature is it's not effective. You want to train a really skinny network with very few filters. It's not effective to build skinny networks and then train them because you get bad minimizers with poor generalization error. So what people do is you start with a wide network and you train that, and then you prune the weights, so you prune the filters, and you condense that down to a skinny network, and then you get good generalization error. And I think that's sort of interesting because you'll see here that these wide networks, the width really convexifies this landscape. It makes it much easier to find these sorts of wide, well-behaved minimizers. And then once you have them, you can just sort of throw out the meaningless weights and get back something high performance. Okay, so what does this mean for optimization? If we have time, we'll try to return to this visualization issue a little later. But what does this mean for optimization? Can we treat neural loss functions like they're convex? I just said, well, well-behaved loss functions, at least locally, they look convex. Can we use convex analysis to say useful things about them? The answer is sometimes. And I'm going to show 2 examples of things that we've studied in my lab relating to optimization of neural networks. In one of them, convex analysis and math that really comes from the convex properties of functions is really informative on how to design good algorithms. And in another case, it's just not. Okay. So a bunch of people have already talked about GANs in this workshop. I'll give you my quick 3-slide overview of GANs. So suppose that you have a probability distribution like a Gaussian curve, and I want to learn a neural network. I want to train a neural network that can represent this distribution, but I'm only going to train it from samples from the distribution. So I take some samples from this Gaussian curve, and I want to reconstruct the Gaussian in some sense. Or maybe you have a really complex distribution. So I have samples from the distribution of natural images, and I want to learn the distribution of those images. And then I want to produce a neural network that can generate new images from that distribution. So I want to create new samples from that distribution. In this case, we trained it on real images that are taken from a real image distribution. And I want this thing to produce fake images that are synthetic. So we cook up a neural network that takes in a random noise vector that we call Z, and we pass it through a generator network that convolves this up into an image. And then we could pass this through some sort of loss function that measures how imagey it is. So you need some sort of measurement of how good an image is. You could use something like total variation, but that won't produce very good looking images. That's not quite fine enough instrument. What you would like is you would some sort of measure of image goodness that has human-like characteristics. And so we'll stick a neural network in there called the discriminator network. And the discriminator network gives us a rating of how good looking an image is. How imagey is it? And the goal of this generator network, when I train the weights in the generator, is to fool the discriminator into thinking that the images it's producing are from the real distribution. So it wanted to the discriminator should think that the images coming out look really good. But if you train something like this, what ends up happening is instead of producing good images, the generator just takes advantage of weaknesses in the discriminator. So there are various adversarial exploits you could make on this discriminator that the generator is going to learn to take advantage of. And so to prevent that from happening, we're going to keep updating the discriminator as we're training the generator. And we do that by training the discriminator to tell the difference between real and fake images. So the generator is trying to minimize a loss function that measures how well it fools the discriminator, and the discriminator is fighting back. It's trying to maximize the same loss function by not being fooled and telling the difference between these real and synthetic images. And we train these things using an alternating gradient descent process. So I want to minimize this loss for the generator weights, maximize it for the discriminator weights. And I can do that by computing a gradient for the generator weights, and then I march down the gradient with some step size tau. And then on the next iteration, I compute the gradient of the loss function with respect to the discriminator weights, and I march up that gradient. Oop, that should be a plus, not a minus. I march up that gradient with some step size sigma. But this doesn't always work so well. You get what are called collapse events. So these are plots of the loss function for the discriminator and the loss function of the generator for DC GAN. And we'll see that as it trains, these loss functions start to evolve in a reasonable way. And then all of a sudden, the loss function for the discriminator falls to 0. That means the discriminator is winning the game. And the generator loss shoots up. And this is called a collapse event. And when that happens, images coming out of the GAN look like this. They're just sort of random noise. So what's happening, the discriminator is dominating the game. The generator can't compete. But we know from convex analysis that we can actually do better than this. So it's known in the convex analysis literature that these kinds of alternating minimization maximization methods are not numerically stable. So bad things happen. When you're just solving a minimization problem, gradient descent sort of gets stuck in these minimizers, and you can't go any further than that. So that keeps things stable. But if you're trying to find a saddle point that's minimal in one direction and maximal in another, then you have updates that are sort of competing against each other. The discriminator, or the generator is trying to minimize, and the discriminator is trying to maximize. And if the minimization updates are stronger than the maximization updates, then you'll never settle into the saddle point. You just fall off the side of the saddle, and you get a collapse event. So these sorts of behaviors are really well studied in the convex optimization literature. So back when dinosaurs ruled the Earth, people studied convex optimization problems, and there's a whole literature on saddle point optimization. So there's this Chambol-Pak method from 2010, and there's similar work from Esser, Zhang, and Chan. And then I even dabbled in this area for a while back in 2014. And here's what the literature on this says. If you want to stabilize this kind of training, you just have to make a very simple change. So I have this descent step and then this ascent step. I'm just going to add in a trivial thing called a prediction step. The prediction step says, after you update your generator weights, look at the step you took between your old generator weights and your new generator weights, and add that back. So go further. However far you just went, go that much further, call that G hat. That's where I predict the generator weights are going to be in the future, assuming the dynamics of the problem doesn't change too much. And then when I update my discriminator, I'm going to update it just like before, except when I evaluate the gradient of the loss function, the value for the generator weights I'm going to plug in is the predicted generator weights. Okay? So it's basically the same algorithm. You just do this simple look-ahead step, and when you compute your generator update, you just plug in these predicted weights. And it's known in the convex optimization literature that this produces a stable algorithm that's attracted to saddle points. But without the prediction method, it doesn't converge, at least not for weakly convex problems. And so we can look at some experiments here. So this is DC GAN images. This is trained with no prediction, and this is trained with prediction. And this is using a GitHub repository we got that had very finely tuned parameters to make this thing converge. And when we look at these, the loss functions for this thing, we see that there's many collapse events. This thing seemed to collapse multiple times, and it just happens that if you stop it at a point that's far enough from a collapse event, you get good results. But if you train this with a prediction method, then it's numerically stable, and you don't have any collapse events. And this is not such a brittle thing, so we can actually multiply the learning rate by 10. So this is training with 10x the learning rate. In this case, the method without prediction immediately collapses. The method with prediction still works fine. These are the loss curves. So you'll see in this case, the learning rate's so high, this just immediately explodes. but this is still really well behaved. It actually trains quite quickly. And you might think, well, that's not such a big deal, just don't use a big learning rate. But actually, the learning rates you need to train GANs are very fine-tuned. And to demonstrate that, we can actually cut the learning rate from the fine-tuned learning rate. We'll cut it by 50%. And when we do that, it also diverges. So in this case, without prediction, the method diverges. With prediction, it still converges. And if you look at these loss curves, you'll see that the DC GAN without prediction is stable for a while, and then it has a collapse event, and it can't recover from that. We've also done experiments with things like weight tuning. This is also very momentum tuning. These training algorithms are very sensitive to the momentum parameter, but we can actually train with prediction and use a range of momentum parameters that's much wider than you can without using a prediction method. So there's a few other test problems. This is trying to learn a mixture of Gaussians. This is learning a mixture of 8 Gaussians arranged in a circle. If you try to learn this distribution with a prediction method, it converges really quickly and it remains stable. But without prediction, it sort of oscillates around and it picks up certain modes and then it switches to other modes. It doesn't really stabilize. And we can actually sort of turn the knob up on this and try to fit 100 Gaussians that are organized in a circle. In this case, the prediction method, it can't quite resolve the difference between these Gaussians, but at least gets a nice circular distribution that overlaps with the Gaussians that we wanted. But without prediction, you get something very unstable. And I actually want to make a video of this because there's some sort of interesting dynamics where these points sort of wave around and they never really seem to converge. It's not a very stable training method. Arthur mentioned yesterday that everyone seems to ask if you can do the bedrooms. I don't have nice curves to show you for this, but in our paper we have some tables that you can look at. But we do the bedrooms, so here's stack GAN results on the LSUN data set. My student said, after the first version of our paper came out, he said that people on Reddit would think we're uncool if we didn't do LSUN. So we did that. So hopefully Reddit now thinks that we're cool. All right. So here's an example of a problem where convex analysis doesn't really inform us very much on how training proceeds. Neural networks are very big. Everyone's seen this chart. It's actually shown up a few times in this workshop. It's just showing the size of neural networks versus the top 1 accuracy they can achieve on ImageNet. And we see that many of the state-of-the-art networks need tens of giga operations to process an image. Oh, and tens of millions of weights. Just doing a quick time check here. Okay, I'll try to wrap it up pretty quick. Tens of millions of weights. But the question is, how do we put these things on low power and embedded systems? Do you want to put this on a drone or a cell phone? How do you fit these huge networks on there? And one solution is you binarize them. So I'm going to take the weights of my neural network, and I'm going to try to force them all to be +1 or -1. Now all of the weights are just 1 bit. And also, there's no multiplications in the network, because multiplying by a weight is just a sign flip. And so if we can do this, going from, say, 32-bit arithmetic down to 1 bit is a 32x compression, although in practice you could probably get away with less than that without using any, less than 32 without any special tricks. It reduces your storage costs, it strips out all the multiplications, and they're really effective types of neural networks for things like ASICs, FPGAs, other low-power devices. So how do we train quantized nets? Well, you train a standard neural network just by computing the gradient of the loss and then marching down with some learning rate alpha. And if you want to train, say, an integer-valued neural net, so I want all the weights to be integer-valued, I want to make sure that on every iteration the weights remain integer. So if I have some integer weights, I might compute a gradient update and multiply it by alpha. And when I add it to the weights, I don't want to change the fact that these are integer, so I put this quantization operator here that rounds this update to an integer. But I need to use a smart update. I don't want to just round to the nearest integer because when alpha, the learning rate, gets small, these updates are all going to be less than 0.5 and they'll just get chopped off. They'll get rounded to 0. So we use a smarter method called stochastic rounding. This is a very well-known method in the hardware literature. It was studied in ICML 2015. And the idea is that if your update is 0.3, then you round it down with a 70% chance and you round it up with a 30% chance. And the expected value of the integer you get back is still that 0.3. So that's a much more reasonable way to train. And the advantage of this is that these kind of training methods require no floating point weights. You can train with no floating point arithmetic at all. But if you want to train with, if you want to train better nets, you have to use something like the binary connect algorithm. And binary connect rounds the weights before it computes the gradient of this loss. So in this algorithm, you use floating point weights. The weights are floating point. But before you compute the gradients, I snap them to the nearest point on the integer grid. And I compute the gradient at that location. And this method is very popular. A lot of people use it. But the disadvantage is that it still requires floating point computations. Even though you're training a quantized net, you have to train using high precision floating point. And what we find, so these are training curves. So these dotted lines are show generalization error. It's generalization error over time for SciFar. No. Okay. Okay, well, the idea is that, I'll just mention a few things here. Okay, so stochastic rounding methods, deterministic rounding is a disaster. Stochastic rounding is better. If we use binary connect algorithm that uses floating point arithmetic, you can get really good. And then this red line is full precision. And full precision networks, with full precision training, you get about 0.8% better than you can do with a quantized network. But you don't do much better. Okay, so I want to study the behavior of these kinds of algorithms, and I can do that using convexity assumptions. If I try to study behavior with convexity assumptions, what I find is that I can put a bound on the error of these algorithms. This is the optimality gap, and it decays over time. So there's this decay term. There's an almost constant term on the top, and there's a t on the bottom. T is the number of iterations. So this term decays, but there's also this noise floor term that doesn't decay, and it scales with this parameter delta, which is the discretization width. So if you have a really fine discretization, you get a better noise floor. But if we look at the, so this is stochastic round, or some stochastic rounding. If we look at a, oh yeah, I had this backwards, sorry. This is stochastic rounding. This is a fully floating point algorithm. With the binary connect algorithm, we can prove exactly the same results. You converge with linear speed up to a noise floor, and that's pretty much it. So we get the same results under convexity assumptions for both of these algorithms. That doesn't explain why one is so much better than the other. And to understand why one is much better than the other, we have to look at the dynamics of these algorithms on non-convex problems. And so what we can do is we can run SGD on a non-convex problem, and the iterates sort of bounce around, and we can plot the equilibrium distribution of this thing. So if you run it for a really long time, here's what you get. I can do it in 3 minutes. Is that okay? Okay. Too late? Okay, sorry. Okay, we can plot the equilibrium distribution, and if we drop the learning rate, we see that this distribution starts to concentrate on these minimizers. If we drop the learning rate even more, it concentrates further. And if we drop it even more, it becomes very concentrated on a global minimizer. But if we use a fully quantized training algorithm, so this is an algorithm that doesn't use floating point arithmetic, we drop the learning rate and it starts to concentrate, and then we drop it more. It concentrates a little bit more, and we drop it again and nothing really changes. So we don't have these sorts of concentration behaviors. And what we can actually prove is that these fully floating point algorithms, like binary connect, they have an exploration-exploitation trade-off. So when the learning rate is large, they explore the landscape, and as the learning rate decays, they sort of aggressively settle into local minimizers, and they concentrate on those minimizers. But you can look at stochastic rounding, which is a fully quantized method, and this method doesn't have these concentration properties. I'll skip ahead a few slides. But in a nutshell, the lack of concentration properties explain the difference between these algorithms. Binary connect requires floating point to train a quantized net, and it gets great generalization error. But if you don't have those concentration properties, these sorts of simulated annealing type global optimization properties, then you get really bad results. And I have some results that I'm not going to have a chance to tell you about in the interest of time, but we can do some more visualizations on the descent paths that SGD takes through these loss functions. So this is plotting the contours of a loss function, and this is the descent path of stochastic gradient descent. And we find that algorithms with good generalization error, so here's SGD with a small batch size, they start with an exploration path that goes parallel to contours. It's not strongly attracted to this minimizer. And as soon as you drop the learning rate, it becomes strongly attracted and it falls in to the center of this local minimizer. But if you train with a large learning batch, so this generates poor generalization error. If you train with a large mini batch, you don't get these kinds of trade-offs. This large batch algorithm is immediately attracted down into this minimizer, and you don't see this sort of 90-degree kink behavior where that exploration-exploitation trade-off happens right here. Okay? Okay, so to wrap up, Neural loss functions are sometimes really well behaved. Well-designed neural networks have really nice loss functions with landscapes that are populated by large, flat, convex-like minimizers. There are still things we don't understand. I don't think we understand these sorts of chaos transitions that happen with deep networks or the effect of skip connections. But I think there's this interesting issue. Is sharp versus flat even the right question? Maybe we should look at things like chaotic versus non-chaotic. And I'll leave you with that. Thanks.